Hi class, this is Camprine 2, or basically it's General Chemistry 2. And as promised, here's your video, basically a review on your stoichiometry and chemical reactions. But before we proceed, I would just like to inform you that when I teach chemistry, it's very heavy on computations. But I decided to handle this course in a different way, so we won't do too much calculations. So I will focus on the applications of your concepts, and most probably I'll be giving essay type exams. So if you just listen to my stories, um, I'm sure you'll do well in this course. But as I informed you, you need to review your stoichiometry and chemical reactions just to check on your background from Chemistry 1. So here it is. So first, we review the concept of the mole. I'm sure you've heard of this. It's not this mole, which burrows under the ground, or it's not this mole that you find on your skin, but this mole in chemistry is this number, 6.02 times 10 raised to 23. So mole is like a unit. So you know that when somebody tells you he or she has a dozen pencil, 1 dozen of pencils, it quickly comes into mind that it means 12 pieces of pencils. So, in chemistry, in the world of molecules, atoms, etc., we cannot count them with our naked eye. So, chemists devised this unit called mole for us to easily count the amount of particles, whether it's atom or molecule or ion. So when we say 1 mole, it refers to 6.02 times 10 raised to 23 of anything. So for example, when I say I have 1 mole of water, and we know that water is H2O, water is H2O, and I say I have 1 mole of water, then it means that I am referring to 6.02 times 10 raised to 23 molecules of water. Okay, so the technical definition of mole is the amount of a substance that contains the same number of elementary entities as there are atoms in exactly 12 grams of pure carbon 12. So carbon 12 is always the reference. So chemists love to use carbon 12 as the reference for anything. So when we say elementary entities, it means it can refer to an atom, it can refer to a molecule, it can refer to an ion, or whatever type of particle we are considering in our chemical compound. So again, the mole, 1 mole, is numerically equivalent to what we call Avogadro's constant, or it's also called as Avogadro's number, which has this symbol. So its value is 6.02 times 10 raised to 23. So in this photo, we see 1 mole of the substances here. So we have here 1 mole of carbon. This is carbon. Basically, it's soot. So it's 1 mole carbon. We have here 1 mole of sulfur. We have 1 mole of mercury. So this is liquid mercury. We have here 1 mole of copper. And we have 1 mole of iron. So for this one, 1 mole of carbon. So we have 6.02 times 10 raised to 23 atoms of carbon. Here, for 1 mole of sulfur, sulfur is usually found as a molecule which has 8 sulfur atoms. So this sample contains 6.02 times 10 raised to 23 molecules of sulfur. This liquid mercury has 6.02 times 10 raised to 23 atoms of mercury, and so on. Okay. Now, I'm sure you're also familiar with the concept of the molar mass. So the molar mass, represented by a capital M, or some references would prefer to use mm, okay, is the mass in grams, take note in grams, of 1 mole of units. So the elementary entities I talked about a while ago. 1 mole of whether it's an atom or a molecule of a substance. Okay, so the molar mass is used to relate the physically or practically measurable property of your matter, which is mass. We can readily measure the mass of any substance, right? The molar mass relates the mass to the amount or the number of particles you have in your sample. Okay, so it says here if you are given the mass of your element or whatever compound, for you to get the number of moles of element from the mass, you need to divide the mass by the molar mass. And then from these moles, you use the definition of the mole, which is this one. 1 mole is equal to 6.02 times 10 raised to 23, let's say, atoms. Okay, so if you have the number of moles, you just multiply it by the Avogadro's number to get the number of atoms in your element. So we will have a few examples later so that you can see how this is performed. But before we proceed, do you know how to determine the molar mass of your chemical compounds? So in that case, you will be needing your friendly periodic table of elements. So for your periodic table of elements, we know that you can get the atomic masses of your elements here. So actually, your molar mass is numerically equivalent to the atomic mass. So for example, if I have molecular hydrogen, so that is H2, I want to get the molar mass of H2. So the molar mass would be the numerical value of the atomic weight of hydrogen, which is 1.008. I multiply this by 2 because I have 2 atoms of hydrogen in the hydrogen molecule. So I get 2.016 grams per mole. So this is the molar mass of the hydrogen molecule. It's pretty easy, right? Okay. So let's proceed with an example problem. So it's asking us how many moles of helium atoms are in 6.46 grams of helium. Let's go for magenta. So it's asking for the moles of helium, and we are given 6.46 grams of helium. Okay, so if you check your periodic table, the molar mass of helium is around 4 grams per mole. Now we are given here grams, right? And we want to get the moles of helium. So we divide the given mass by the molar mass. So we divide this by 4 grams per mole. And if you use your calculators, you will get a value of 1.615. Now, I'm very particular about the units. So notice here we can cancel the gram and the mole goes to the numerator. So we end up with the unit moles. Okay, so this is the answer. Okay, so we can move on now to the next sample problem. So determine which of the following contains the largest number of atoms. So we are given masses of helium, iron, and mercury. So we're going to be needing their molar masses. So just consult your periodic table for the molar masses. And if you recall, so the flow will be from the mass of the element. We divide it by the molar mass to get the moles, and you multiply the moles by the Avogadro's number to get the number of atoms, or basically particle. So let's try with this problem. We need to compute for each element. So for helium, we are given 7.68 grams of helium. So we need the molar mass of helium, which is 4 grams per mole. So notice I inverted the molar mass. A while ago, I divided it by the molar mass. So if you go back to the rules in your basic math, if you are dividing by a fraction, it's also the same as multiplying it by the inverse of the fraction. Okay, and then this will give us the mole. Then we multiply the mole by the number of, by the Avogadro's number. So 6.02 times 10 raised to 23. So atoms in this case. So by definition, you have this number of atoms per mole or 1 mole. So if you use your calculator, this will give you 1.16 times 10 raised to 24 atoms. So that's a very, very large number. Now let's go to iron. So we have 112 grams of iron. Look at your periodic table. The molar mass is 55.933 grams per mole of iron. Got the E here. And then again, we multiply this by Avogadro's number. Per mole. So this will give us 1.21 times 10 raised to 24 atoms. Okay, then for the last one, we have mercury. So 389 grams of mercury. And its molar mass is 200.59 grams. Per mole of mercury. Then we multiply it by Avogadro's number. Per mole. And this gives us 1.17 times 10 raised to 24 atoms. So our answer is letter B. So 112 grams of iron has the highest or the largest number of atoms.